Good morning, everyone, and welcome to our first seminar of the NLA series of Projects in Practice. I'm Peter Murray, I'm Curator-in-Chief at NLA, and this is part of NLA's new Building Better programme, looks at supporting the built environment professions to improve competency in technical design and delivery of new buildings in London. We'll have monthly seminars, including in projects in practice, which will present best practice case studies and the products that define them. And then we're also going to have technical competency briefings, which provide an overview of the latest legislation, regulations and technology. And in today's seminar, we'll hear about two projects that were featured in our recent NLA report on Zero Carbon London. And we'll be presenting in detail the low carbon design approaches and materials that have been used. So before we start, I'd just like to remind you that there will be an opportunity to ask questions of our speakers at the end. You can post those questions throughout the event using the Zoom Q&A function on your screen, and we'll try to answer as much as we can during the Q&A time at the end of the session. Now we're going to go to the first project, 16 Chart Street in Hoxton. And we have Hayne Tillett Steele, who will give three presentations focusing on different elements of the scheme. And to start off with, I'm going to hand over to Mark Tillett, who's a director at HTS, who's actually on site to do the presentation and will show us around. Mark, over to you.
Hi, good morning, and thank you very much for joining us on this cold December morning. I'm Mark Tillett from Hayne Tillett Steele. We're a structural engineering practice. Thank you very much for the introduction, Peter. I didn't hear any of it, but I'm sure you said nice words. As I said, we're Hayne Tillett Steele. We are NLA Net Zero champions, members of the UK Green Building Council and LETI. And I just really wanted to say with an expression you hear a lot now is the time for refurbishment is now. I mean, the time for refurbishment in our eyes has always existed. We've been doing remodeling of sites our entire careers, and it should always be the first port of call on a project. A number of examples locally to this building. We've recently finished the Standard Hotel, 60 London Wall, 160 Old Street and 77 Coleman, all of which fantastic frames, good bones that we built on. And this is really what we've got here. So the challenge we had as a business, we had grown to nearly 100 about 2 years ago, and we had outgrown our current building. We're now 130, so 2 years ago we started looking for a new office premises, something bigger and something better. And we found this. Well, not this, but what we found is what sits below us. And we'll just go to some slides now, and you can begin to see how we started out. So this is 16 Chart Street, just off Old Street roundabout. The site prior to the 1930s was terrace housing. There was a cemetery for a hospital. So lots of kind of history. This building was built in the 1930s below us. It is a concrete floored, beam and hollow pot, steel framed structure supported on pad foundations with load bearing masonry walls to the perimeter. So a nice, simple structure full of character. And there was no question we were ever going to take it down. As you can see from the photos, quite a drab 70s style office interior, the kind of beige air conditioning units. But we soon stripped this back and just saw just how much potential the building really had. Fantastic steel sections, a really good grid, amazing natural light on all the elevations, just pouring in a detached building with naturally lit on all the elevations. One key thing we wanted to do was minimize any demolition, so keep as much of what exists. So the only things we really took away were the flat roof and also just you'll see as we go down the building, the stairs to the lift core, and then we repurposed that as a toilet block. Just the slide before this, you'll see we did some investigations in the foundations. This is the first stopping point really. So you really need to understand the grain of an existing building before you can come up with your proposals, because you work out the grain and then you can work out what you can keep and how you can really sweat the structure and make it achieve its full potential. So just going forward, you can see three images here. On the left is the original 30s building. The image in the middle, the slide in the middle, is the consent that was achieved in 2017 with a flat roof. And we came on board in 2018 and just thought, we can do something better here. It's a great site. And so one of the first decisions was to do a Northlit roof structure, which makes a huge amount of sense. As many of you will know, you get all the benefits of the skylight with the shade. And then if we go forward, this was the first move. So you can see the original building. This is the final proposal. And then how we got to that proposal. So the host building, you can see there is number 1 in the middle. The first move was getting consent for the Northlight roof extension. Then we got consent for a basement, and this was all kind of piggybacking on each other. The basement was kind of an unavoidable necessity, really, just for future storage, future adaptability. And then the third addition, which came on very late in the day, was the side extension. And I think, like anyone who's done their own house up, you know, a lot of the best decisions come along the pathway. And I've said this before, I think great design is not a line in the sand. It evolves, which I know project managers and contractors don't like, but a lot of the best ideas come as you really get within the bones of the building. Okay, so construction. This is the initial basement construction, which led. You will see more of this as we go around for a little tour of the building in a minute. But very simple basement construction. This was the roof which came off the existing building. We left just effectively the top deck. We put CLT back here, and you'll see that very shortly. A top view, the load-bearing masonry walls. This was probably about a year ago, these shots you see now. The CLT started going in. It's very satisfying, very quick to erect. There were a number of issues of building with CLT, which we found on this job as well, and we'll touch on a couple of those. One is waterproofing, the other is staining it. And if we just keep rolling through, I think, yeah, I think we have some drone footage coming up, which was taken about 2 months ago, and it'll give you an idea of the building from the outside. And then we're going to do a quick walking tour of the building and see some stuff in the flesh. Okay, Andrew, if you can run the drone video, that would be fantastic. And just as that's gearing up now, what you could see there is a plan showing a section through the building and how it's become COVID compliant. Okay, so now the drone is on the top floor space. It's just working through the north lights, going through to the outside of the building. It's a mass timber structure on the top floor, so no steelwork. The sawtooth roof profile of the north lights, and there's an opportunity, we haven't used it yet, to put put PV panels on those south sections of the north lights. A bit of flappy cladding there. It was still just awaiting practical completion, and this is really thrilling. Just on the video there, you can see the CLT walls and slabs being erected on site. It's incredibly quick to go up. They got the whole elevation up in 3 days, and it's almost as satisfying as a traditional building being plastered. Just overnight, you just see a transformation. And then as we pan around to the northern elevation, there's one dominant roof light, which I'm standing under now, which is our rather daunting presentation area. And then 3 smaller roof lights, north lights, which run out. Okay, and I think that gives you an overview of the building. We're now going to just walk through the space. So this is our kind of town hall space. You're just going to walk through the space. Sorry, this is our town hall space as a building. So mass timber construction, big hardwood Baubucker glulam beams which span 10 meters across the space, which support CLT panels. These are nearly 7 meters long. This is the most dominant north light. We'll have all of our kitchen and cooking facilities there. And this is a space which really is the kind of common room for the whole of the practice. As we look down into this area, this is our accommodation stair. This was another late addition, but we're so glad we did it. We have no shortage of vertical circulation here, but this just opens the whole thing up and has this wonderful CLT top hat to it. So we're going to walk down now, just pop into the extension and then just walk over the height of the building and pick out some of the delights of the new structure and the existing structure. So the CLT, it's going to be whitewashed, which serves as a fire retardant as well. Here we go. So this is the side extension, which was the latest addition to the scheme. One of the big challenges with CLT is control of water during construction, and it wasn't resolved here adequately, and we had staining and all the B&K and are very good at actually removing it. But it's a bit of a pain. It can cause localized warping, and it can also slow down your finishing trades. Another tricky thing to get right was benchmarking on the whitewashing and the finishing. We do samples, but as a natural product, it always comes out slightly differently. Yeah, every project, I think everyone gets better and the industry gets slightly better at dealing with those issues. So we're going to pop down now to the first floor, down the accommodation stair at the back. Our lift shaft is going up here at the moment. This will become the accommodation stair, being delivered just before Christmas. And this will really become a breakout space, I think. It's uninsulated, but I think it's sheltered from the wind. They have a huge polycarbonate screen here, so they'll be flooded with light. And we see people using this for a chat, just to chill out a bit or make a private phone call. We'll just take a quick peek in here. This is this was the flat roof, so this went back as a CLT slab onto steel beams. The beams are spanning about 10, 11 meters. So we looked at doing it in timber, but it was just too deep. So we've gone with a steel frame, built off the existing frame stubs just below these columns here. I think it's worthwhile just touching on the raised floor, because this is something which it's a real bugbear of mine, raised floors. And I think in a few years they will be designed out. And we wanted to get rid of it here, but fundamentally there was just too much stuff to go into the floor space to allow that to happen. But I think in terms of, I wish what we could have done better in a few years, that will be one of them. And I think there'll be a big market for retrospectively removing raised floors and adjusting stairs and lifts to suit. Okay, so we're going to go down now to the first, let's go down to ground floor actually. And you'll see some of the kind of found delights of the existing structure. So this becomes our reception space, this is a beam and pot slab, and it is quite unique insofar as there was no render on the soffit. It was just some leaded paint, which we had to remove anyway. And what remains now, what exists is this kind of wonderful kind of terracotta finish. And the only finish we've applied to any of the building is really this pea green paint on the original steelwork frame. So none of this needed strengthening. As I said earlier, the key thing is to do your investigations as quickly as possible and find out, you know, what could let the structure dictate in some respects what you're doing to the building and where you extend up. So this has ample capacity. You can normally take samples and prove steelwork well beyond its original design loading. Okay, if you look down into this space here, this will become our library and meeting room area. One of the slides you saw flashed up quickly earlier was the evolution of the design through the pandemic. So it's kind of been a bit of, we've been lucky in a way that we could change things on the hoof. So we've introduced some kind of breakout spaces. But fundamentally, what we found is all the stuff that people are looking for, natural light, natural ventilation, big open spaces, not hot desking, we already have. We also have 60 bike spaces here, which is 1 per 2 staff, 5 showers, so kind of record-breaking stats. And I think the biggest challenge, now we have a vaccine, is actually getting people out of their homes and into the office, because people have a choice now. And we need to make the office environment somewhere better to work than home to get the collaboration going as much as we can. Okay, so just to finish off this whistle-stop tour, we're going to have a quick look out into the yard space. This will be our kind of grand entrance. Again, CLT exposed to the elements. as a soffit to our first extension floor, sitting on a kind of a concrete base here, and then down into our yard itself, which is going to be a nice external space, although it doesn't look it at the moment, it will. And there's lower ground floor here. We won't go in there, but that's all of the kind of engine room of the building, the showers, the meeting rooms, printers, IT. And this is the basement we created, really. High carbon costs, but we couldn't really avoid it. We wanted a building that was adaptable for a huge time to come. This is nearly 100 years old, and we wanted losing connection. Okay, so I'm just coming out of the basement, but what you would have seen is a fairly unique underpin where we have used it as the kind of formed struck finish. We haven't put any liner walls in front of it. There's no waterproofing, so we're going to rely on natural ventilation, and it maximizes our area, minimizes the carbon. So using underpins as a finished face, it's the way to go. They've achieved an absolutely fantastic finish here. And this basement space is going to become a gym of sorts with rowing machines and cycling machines and storage for PPE and all the rest of it. So we're just going to finish now, just going to the outside of the building and looking back. So you can just see what the elevation looks like. As you can see, there's lots of activity happening on site. Morning, guys. And we are due to move in, we are told, on March the 1st. So this is Chart Street. It's a very residential area. The residents have come back with, kind of applause at what they've seen erected. So they seem to be fairly happy. This is the extension elevation, and you can see the main building with the Northland construction over the top. And now I'll hand you back to the studio with Andrew and Laura. Thanks a lot for your time.
Thank you. So we're just going to, Laura and I are just going to run through some of the technical design details and just the embodied carbon story, picking up from where Mark finished with this sort of front elevation of the building. And I just want to talk through some of the key design decisions around the level 3 structure, the roof extension, and then also looking at this side extension and external core and the decisions we made as we went through the journey. So early on, a lot of discussion, Mark mentioned about removing the existing timber roof. There wasn't an opportunity to use that, both at Falls, it was in bad condition and just couldn't take the weight. But, there was whether we looked at more of a composite, RC slab, a steel, you get all the benefit of the concrete and the steel working together. But it just, just the sort of feel of the space, the wellness, the idea of using timber didn't feel right. And obviously the carbon story with it. So then there was a lot of other options, whether looking at CLT, full CLT with glulam beams, the issue being that the depth of those beams got a little bit bigger. Looking at steel and CLT or looking at rib slabs. So we did a lot of work just to look at these different options, model them through, think about the carbon, think about the general implications on the space. And ultimately, we settled with using a CLT on a steel beam so that we could benefit over these larger spans with a shallower steel beam. And I just want to talk through some of the considerations we made between, do we put the CLT above the slab or within the depth, or do we go with a rib slab just to help limit the CLT and obviously use those ribs as a sort of play on the hollow pots lower down to strengthen those areas. So first, just looking at the rib slabs. The benefit here is you're putting the structure where you want it. So in the same way you had the clay pots that had those RC rib beams in between them, using these ribs here. I think one of the challenges is, though, the shorter span you're spanning is only about 4.5 meters. And so in reality, you can kind of make the CLT span. So there's kind of more of an engineering purity about actually just let's stick with it. Let's make the CLT. The other thing is some of the challenges is around the fire itself, in that to get these ribs looking particularly elegant, when you're at 6 meter spans plus the sort of span depth, the ratio of them, the size, it starts to look right. But here, doing that same size, they were getting so small that they're sort of charring themselves from both sides. And so you end up having to, instead of having a sort of nice slim 60, 80 mil thick CLT, you still end up with a thick CLT over the top, which can take, in the fire case, the load. And so things just didn't quite work. Now we think we've got other projects where we have used ribs. We think it's a great solution because you're putting the material where you need it. So you're reducing other wastage of material. But in this case, we decided to move away from that. Then the other key consideration was, do you put the CLT in the depth or not? Obviously, if we put it in the depth, you can partially put it in the surface zone. Can you look at reducing the overall build up there and what you have? I mean, some of the key considerations, again, fire here, thinking through the steel, but also acoustics, because that joint in the sort of sketch where you're going through the steel, there's quite a weak acoustic joint. So how do you seal that? You also have to think about the buildability. You've got to start adding things like angles and what have you to put it in. So although this has a slightly deeper section, slightly lighter when we think about probably the sort of carbon, the steel, when you add in all the brackets and all the other gubbins, that actually it wasn't too different just to put the CLT on top. And what that also did is elevate the general soffit centrally. So you had a better feeling for the space. So we did quite a lot of visualization just to understand that inside. So some of the other key things then is when we're looking at the steel, is thinking about the detailing of the joints, but also just, visually. So to get these beams as efficient as possible, we made them span from the north to south elevation with a single support on that central column. So they were a continuous beam. But what that means is you've got a bending moment, a hogging moment over that central column. So we needed to design this for a moment connection, but it did allow us to reduce the size of the beam, reduce the depth on the space, but also, reduce the amount of material we were using. And so we then had to just think about getting this splice hidden and just chamfered in. Then you can also see the vertical plates on the column. So again, another key thing when designing around CLT is just thinking about those connections, because often those connections can dictate the size of the timber, the need to have enough residual timber around so that you can't char from the inside as that steel gets hot. So making sure, and in this case, that did mean the columns were slightly bigger than potentially the size to deal with that connection. Then you can see here, this is on the front elevation. You've got the existing parapet and the line. And again, the sort of same with the column connections, you've got the main primary roof load coming down. But a big challenge here is that we need to offset the sort of image in the bottom right corner between the CLT line and the masonry so that we can get the insulation, the cladding line, and enough of a cavity. So what it brought is the line off of the building. Now, around the other sides, we were able just to land the CLT into the existing concrete ring beam that exists there. But unfortunately here, just both the condition of that beam and the sort of reinforcement, we couldn't do that. So the decision was made to do these transfers that take the load straight back down into the piers. We looked at sort of doing a CLT transfer beam, but just again, the sort of efficiency of materials. I think it's good to play and look at the different options. It just didn't make as much sense. So then just jumping onto the roof, and Mark was talking about the north lights and some of the challenges. So, one of the obvious you can see with the arrows there is you've got these diaphragms, but they want to flatten because everything's on the angle. So the beams, the main beams, that some of them they're spanning at almost 11 meters. You both need to take the vertical over the roof, but also thinking about that flattening and dealing with it. But just generally, along the bottom there, thinking about the connections, the detailing, the fire, the acoustics, vibration, and also the buildability. And I'll talk about the Balbooker as well, about the need for strong water management plans. So those main beams, an early sort of thought, we did look at a steel beam, but really wanted to keep this in, felt it was right to do this all in timber. So the initial options were looking on the left there at like a glulam beam or an LVL, which is a laminated veneered lumber. But then we started to consider actually maybe these primary beams, we can change them and use a Balbooker, which is a hardwood LVL. And you get almost twice the strength out of this. And so it really, in those longer spans, starts to really come into its own. And we saved about 150 mil in depth. So, if you've got a planning envelope that was already there, achieving that extra height. The other thing is that sideways force as the CLT pushes it, again, just gave us a better, more efficient section. I think one of the big challenges, though, with Balbooker is that the hardwood is more susceptible to moisture, so it had to come wrapped to site, and you really do need a careful water management plan. You can see here how it sits right in the bottom beneath the sort of the guttering and the gully there, and so really dealing with that water on site. We had a few challenges, especially during the initial lockdown, of making sure you've got heavy rainstorms and making sure you're clearing that water out and dealing with that. Then just moving up then from the Balboca, then thinking about limiting the amount of framing we have to support the CLT. So we looked at different steel options. You've got a channel there on the left, or a very simple, just a straight plate. We also looked at a fully timber option, but it just started to become a bit too much like a sauna. What we ended up with is actually using the sort of T section on the right. So, and just looking, and part of this is that was put in the least amount of material, but trying to work with what we had. So the width of the T aligned perfectly then with the window, so you had a very clean line, and then the fact that the T was recessed on either side allowed us the lighting, so the sort of the electric lights that we're putting in allowed those to be sort of LED lights to recess there, and then the other thing is actually just looking at the glazing. Do you want the glazing to be supported on these T's, or does it span top to bottom? And we did some work there, just trying to figure out to make sure what would be the most efficient and least carbon version of that window. And it was decided actually getting them to span top to bottom, so that you just had a smaller restraint on here, meant these T's could just take the axial load and the windows themselves could be much more efficient. And then the other big thing is just thinking about, you could probably see when you walk around with Mark on site, just common datums, but very much how you articulate joints, how you express them, how you think about the grade of timber. So there's a lot of work just thinking about how do we choose the right grade of timber, chamfer joints, so that you can have this very common data and just think about how it goes together. And you can sort of see the transition there from some early sketches to what was drawn. And then just finally quickly looking at the side extension, a couple of things here. One, again, you can see the sort of blue line on the left image at the front of the page with the arrows. So with this, again, this sort of big north light wanting to push out, wanting to flatten out, there was a need there to actually put in a, to avoid over sizing lots of the timber and big beams. We actually had a very small sort of channel steel section there. And what that did is we could get a push pull off the lower floors, and that just allowed us to stop the spread, so that the cladding didn't have to be over designed to deal with a tie. And then on the right, the little arrows just showing design a glulam beam along the edge, which supported the cladding. Then the final thing, just to quickly show, is a couple of sketches around the external stair. Now, obviously, it's a steel stair, and you could argue, if you're looking at embodied carbon, why have you done in steel? But we did look at different constructions. But ultimately, I think, looking at how can we reduce and make this as efficient as possible? So the structural members are efficient. We looked at a cantilever option on the left, and then actually just using the cladding rail as a prop column in the corner in the middle option, which is what we adopted, so that we strip it back to the base of materials needed and make sure everything's considered, and the parts, it's not lots of different members. We're using more commonly available sections. We are designing it as efficiently as possible. And that's kind of, I think, a key, another approach to this, that, using the right material, but then using it efficiently. Now I'm going to pass over to Laura to talk about the embodied carbon story.
Thank you. So I will be talking about the sustainability aspects of Chart House from the perspective of whole life and operational carbon. So as a briefly introduction, the embodied carbon is all the carbon associated with the materials. It accounts for raw material extraction, manufacture, transport, construction, but also maintenance and end-of-life demolition and disposal. And operational carbon is the energy used to power, heat, and ventilate the building. The accounting method breaks down a building's life cycle into modules. So as you can see on the right, module A is the manufacture, transport, and construction. Module B is in use, and module C is end of life, so disposal and demolition. Since we're a structural engineering consultancy, we measure the embodied carbon for the structure only, since these are the elements that we have control over. So the structure, for instance, the beams, the columns, foundations, the walls, are designed for a lifetime equal to the building's design life. We do not expect them to be replaced. So the bulk of our embodied carbon occurs up front in module A by practical completion, so before the tenants have moved in. We do not measure modules B and C in our own analysis. So for that, we've enlisted the help of KLH sustainability consultants who've provided a whole life carbon analysis. They cover the aspects of the embodied carbon that we are not able to measure, such as the architecture, the finishes, the replacement, and the end of life, and also the operational carbon. And I'll just briefly show the results of these analyses. and identify some of the heavy hitters from the rather unique perspective of being the tenant as well as a consultant. So 5 years ago, we started the HTS Plus carbon counter, which we now use on loads of projects. It works within Revit, and we also have carbon rates for materials based on environmental product declarations, analysis of our supply chain and construction processes on previous projects, all backed up and supplemented by the ICE database. These cover Module A only, as I previously said. So for Chart House, the total embodied carbon of the structure is 244 tons of CO2 equivalent. This includes a small amount for demolition, about 20% for temporary structure, such as scaffolding, and then the rest is the new structure. So putting this into context based on the scale of the building, the total per square meter of gross internal area is 171 kilos per meter squared. Comparing with the RIBA, LETI, and iStruct targets for 2025, which is the closest to the year of practical completion, which will be 2021 for Chart, we can see Chart outperforms all of these targets for the structural embodied carbon. Chart House performs really well in embodied carbon, which is mainly down to two things. Firstly, that 86% of the existing structure was retained. So we essentially took a 90-year-old building and gave it another 60 years of design life while making it fit for purpose for today's office needs. And also about half of the new structure is timber, which is inherently lower in carbon. It also has the benefit of temporarily storing, and by temporary I mean for the lifetime of the building, so for 60 years. It stores carbon within the structure while the building is in use. And this is a really important point in the context of a climate emergency where we have to rapidly decarbonize in the next decade or so. So KLH did an analysis of the whole life embodied and operational carbon. This includes the Module A for other disciplines, such as the architecture and the MEP, and then the carbon associated with modules B and C, so maintenance, repair, replacement, and end-of-life disposal. They've also calculated the projected energy demand for the building throughout its 60-year lifetime. So the embodied carbon whole building is 614 tons of CO2 equivalent, and the operational is 728 tons of CO2 equivalent, which is the cumulative over 60 years. And this is assuming the second most pessimistic of the national grid's decarbonization scenarios. So this shows us that the trade-off of using the existing structure is manifested in the fact that the operational carbon doesn't meet RIBA and LETI 2030 targets because it's harder to embed efficient energy strategies in a reused building. KLH have also combined the LETI and RIBA embodied and operational per meter squared targets into one number, and Chart House just falls short of the RIBA 2030 target. So both analyses found items with relatively high carbon costs. So the top three in structural embodied carbon are firstly the new floor, the new third floor and roof extension. But this is the most significant intervention. It's added over 250 square meters to the space, and per meter squared, it's still less than current benchmarks. Plus, this is where all the this is where a lot of the timber is. So there's a lot of sequestration associated with this extension. The basement is a slightly different story. It's added 58 tons to the embodied carbon. And we know from experience that basements tend to have a high relative embodied carbon because they require lots more structure, like retaining walls, footings, and they need to be constructed in concrete. So the basement at Chart represents 58 tons of carbon, and it adds 65 meters squared. So it's almost 900 kilos carbon per meter squared. However, this is still really useful space. It's got plant and bike storage. The plant storage might otherwise have been located in a less hidden area, which could have been a planning issue. The third heaviest hitter is the external stair. As Andrew mentioned, it's made mostly of steel, which has a high carbon per ton. However, this is mostly dry construction. It's bolted. There's no screed. So the potential for reuse at the end of life is high, although this is beyond the scope of this analysis. And KLH identified heavy hitters in terms of the whole life embodied carbon of as the steel windows, because they've got the replacement cycle, and also because of their material. And they have also found that there is no insulation to the interior walls for an exposed brick finish, and this has actually significantly affected the thermal energy and carbon performance of the building. So just to finish, the lessons learned, mainly from our perspective, has been understanding the interplay between embodied and operational carbon. Since we're structural engineers, we don't typically consider operational carbon and how the structural design decisions can affect the whole life energy use of the building. So this exercise has really helped highlight the fact that reusing a structure is great for embodied carbon, but it makes reaching operational targets that much harder. An equivalent steel and CLT new build, you can see on the right-hand side, would have cost more than twice the upfront embodied carbon. This detailed whole life carbon analyses have identified several heavy hitters that have relatively high carbon impacts, such as the steel windows, the basement, and the absence of insulation to the walls. And one of KLH's recommendations was for us to monitor the energy use once we occupy the space, which we will be doing. And as the end user, as well as a member of the design team, the tension between the lowest carbon solution and the desired solution was a bit more apparent here than in other projects. But this is a fit for purpose and really adaptable space that we're all very excited about. And so just in conclusion, by reusing the existing structure and using lots of timber, we've massively reduced the upfront embodied carbon, which we consider a success in the context of a climate emergency. So with that, we hope to see you in the office next year.
Great. Well, thank you very much, Laura, and thanks to Andrew and Mark, and also thanks to Mark's cameraman, who I thought followed him very well down the stairs there and kept him in focus. So thank you for that. And it's great to see some real live action in our webinars now. So I'll just say to everybody, do put your questions into the chat box so that we can have a bit of a discussion after this next presentation. So we're now going to hear about second project, which is the Institute of Physics on Caledonian Road, King's Cross. And we have Tate Hindle and ACOM presenting. First of all, we have Harish Ratner, Director at Tate Hindle, and he's going to start with an overview of the scheme. So Harish, over to you.
Thank you, Peter. So thank you for the opportunity to go through this project. I think in the future, hopefully we can now visit the building in real life, which is an opportunity which most people can have, as there are exhibitions kind of happening, hopefully next year when we all can get to real buildings. So the Institute of Physics was a new headquarters. Their original headquarters was on Portland Place, next to the RIBA. They sold the building to the RIBA, another institute, which they wanted to do, to another institute rather than a commercial body. And they wanted to come to a new home. And the new home wanted to be a more welcoming space, a space which had something which was really against their existing building, which was a Georgian terrace, not really a welcoming building for school kids and the public. So they chose King's Cross. So go to the next slide. King's Cross as their venue. So the Institute of Physics are a charity, and their aim is to empower physicists and promote physics to all, from school kids to universities to industry to government. So their ethos is really getting physics out there. Okay, next slide. So the design objectives for the building, as I described, is to have a more open and welcoming building. They wanted to showcase physics and how sustainability is going to be part of physicist inventions, such as PVs were invented by physicists. So they wanted to demonstrate that and explain that to the public and kids. They wanted to have a more integrated and welcoming building. So they've chosen a location which is in the Knowledge Quarter which helps to gather people from all different parts of the UK and Europe, but also to the local community as well. It's in a slightly run-down area of Islington, and they wanted to come into an area where they can welcome people who normally wouldn't go and visit an institute. Next slide. So as I said, it's in the Knowledge Quarter. The Knowledge Quarter has a number of its kind of peers there, and the peers are University of London, Birkbeck, Wellcome Trust, Crook Institute. So they are amongst the right location for where they want to welcome other people to come cross-fertilize knowledge. Next slide. So the previous building is a collection of 7 rundown buildings, and they have been adapted over 50 or 60 years, from the 1900s, 1950s, 1970s and 1980s. So it was a hodgepodge of small extensions inside, modifications, so a real rabbit warren. The basement area had a head height of 1.8 meters, so just about my height, so it wasn't really usable. The roofscape was very fragmented, so we took the decision to modify the facade. It's in a conservation area and surrounded by listed buildings as well. So get to the next slide. So these simple diagrams just show some of the key elements. The existing massing is number 1. So our principal extensions were going up 1.5 stories and going down almost half a story. And then option 3, diagram 3 and 4 show the key moves, which I'll go into more detail later on in terms of how the building is ventilated and also how it's lit and how the facade is changed. We kept the facade to Caledon Road and Bath Street, which is on the rear, and then dug down. So the structure inside was completely new. Okay, go to the next slide. So this just gives a little insight in terms of the layout. The layout follows the site form, which is on Caledon Road to the bottom and Bath Street to the top. So it's in a V shape, and the V shape at its heart has a atrium space. And that atrium space has a north light, and that faces directly north towards community gardens, which are residential community gardens to the north. So that really forms kind of the shape which is consistent across all floors, and that forms the heart of the building. And that space is visible from anywhere in the building. So when I'll show you later on the photographs, you'll see that the original building for the IOP was a Georgian terrace with several floors where communication was very difficult. This is a V-shaped plan with an atrium at its heart where everybody can see each other, from the exhibition areas to the office floors to the seminar spaces. Okay, go to the next page. So we call this sort of our sustainability section. So this will really show how the building kind of works. So from the outside, obviously, we've tried to improve the existing fabric. Where there's existing windows, we've replaced those where they were non-original to be more thermally efficient, insulated the walls, and then created a much more efficient fabric to reduce the demand. And then we're looking at the roof. Any areas of roof which were available, we put PV. So 70% of the roof has a PV array on it, and the other part has a biodiverse roof. So it's a green roof and a blue roof, which the blue roof is used to kind of retain water, and they're going to feed that down. The chimneys you'll see in a little while are the ventilation system. So that those chimneys draw air in from the top and then take air in. The air goes through the raised floor plenum, and it comes up, and then as the stale air is kind of built up, it comes out to the top of the windows and into the atrium. And from the top of the atrium, there's a heat recovery plant which takes the air and recovers the heat and kind of feeds it back. There isn't a set of chillers or any other cooling on the roof. All the heating and cooling is provided by borehole cooling. So John, in a later part of the presentation, will go through more detail some of these aspects. Okay, go to the next page. So here is the front elevation. So here you can see the manifestation of the chimneys. The chimneys are on the party wall lines where the original brick chimneys used to be. There are a number of sort of buildings in that area which have tall chimneys, which obviously were in the past polluting the atmosphere where they were kind of coal-fired. So our view was to actually reverse that and actually have clean air coming down the chimneys rather than smoke going up the chimneys. So they provide all the ventilation to the building. So they come in for each kind of bay. On the left-hand side, you can see the bay, which is demolished, which is forms the entrance. And then you've got the three windows are one of the original, non-original facades. And then the two terraces you see at the end were actually original facades from the 1890s. Okay, if you go to the next slide. So this just shows the approach view from the south. You can see the chimneys to the north, chimneys at the upper floor. So they have quite a depth to them. So they, because they have a depth, they can help to provide shading from the sun. So the upper floors, the glazing shade the glazing, but also probably provide modelling, and the chimneys actually reflect the functionality of what they are. The building to the foreground is was a pub. Now is recently been acquired by the Institute. So that will be the next phase for the development, which would be for a maker studio for children. So it'll be an education centre for young kids from primary school to secondary school. So the primary school children will be at the ground floor, secondary children on the second floor, and apprentices on the upper floors. So that'll be the next phase, and it'll be the next method of developing the building, and it's a community engagement. Next slide. So I'll run through just some layouts in terms of how the building kind of works and manifestation of the some of the materials inside. So this is the ground floor. The entrance you saw is on the left-hand side. The desks and the suites on the right-hand side are incubator centre. So the incubator centre is an affordable workspace. And that workspace is managed by the Institute for graduates. So if a graduate has a startup, they can hire that desk and that space at a very highly discounted rate. And then they can cross-fertilize with each other, but also get support from experts in the building and experts who come to visit. So that is a key driver for engagement. So it's merging education as well as startups and new industry. Go to the next page. So that's a view of the entrance lobby. So you can see there we've got a staircase with daylight that welcomes you up to the building. So there is a walk-up staircase. You don't really need to use a lift to go up 3 floors. So that staircase acts as a welcome and invites you to walk up, which most people tend to do. The soffit you can see is concrete, and John will come on to how the concrete is used as a cooling method for the building. And it's unfinished, it's just cast concrete, so there's no other finishes on there. On the right hand side you can see interactive screen. That interactive screen provides a lot of information about the events in the building, but also how the building's performing. So the data in terms of the performance of the building and how that is working is fed through the BMS into that screen, so you can see how the building's performing. It also shows data from the rooftop climate sensor, which sort of shows how the temperature is, air pollution. That's kind of monitored by the Institute, all the way to monitoring cosmic rays. There's a cosmic ray detector on the roof, which sort of shows how that's what the level of rays and input that's getting as well. Next page. So this is a view from the incubator centre. You can see it's an open breakout space with a shop window effectively into the high street. So it's really a shop window for people to sort of see activity and see and welcome people into the Institute. The two lights you can see, which are in perspex, are what is a prototype for created by the University of Edinburgh for Li-Fi lights. So they place these lights in the Institute as a prototype. These Li-Fi lights effectively provide Wi-Fi for laptops, iPhones, etc. But it has 1,000 times the capacity of Wi-Fi. So that's really, again, a signal for how the Institute wants to work, showcasing physics, showcasing new inventions, and welcoming startups like graduates who've invented this into the building, and of course fertilize with other graduates and other industry. Going on to the next slide. So I'll go through the lower ground, which was effectively a basement. The existing basement, I said, was 1.8 meters deep. So we had to dig down another 3 meters to get a lecture theatre. So the two main functions there are a lecture theatre and exhibition space. And then the other facilities are ancillary showers and showers and toilet facilities. So you go to the next slide. So this view shows a view from the balcony, from the reception, overlooking the exhibition centre. So on the plan, you can see a Fibonacci spiral, again, sort of demonstrating physics and science. And this is a photograph from the Moon exhibition, which ran through all of last year. Really a welcoming exhibition for children to come in and learn about physics, learn about rockets, learn about the story of the moon landing. Go to the next slide. Yes, it was a very a popular event, really engaging. The Institute has a engagement team who go out to different schools and show little experiments, show encouragement to kids who normally wouldn't get into STEM projects, STEM education. Sciences, and welcome them into the Institute and that line of education. Okay. Next slide. And this is the lecture theatre, where, if you imagine, this area was 1.8 meters high, and so we had to dig down to create a lecture theatre, which is a flexible lecture theatre, which provides 170 seat lecture theatre. The soffit, again, is exposed concrete to provide some of the cooling. There's cooling in the floor to supplement it for large numbers of people, and a flexible space where it's got a roll-down screen. So that screen is a roll-down screen at 12 meters long, which can be rolled up again, and then the space can be kind of reconfigured. Okay, next slide. So I'll show you the office floors. So this layout sort of again demonstrates the layout of the V shape. All the desks are arranged, so there's a view from a desk. There's a view from a desk within 7.5 meters, either for a window or into the atrium space. On the first floor, there's a terrace which kind of overlooks the kind of community garden. Go to the next slide. So this view shows a view from the typical office floor. Some of the key elements here are, you can see the concrete soffit providing the cooling at the top, and the grill at the bottom is the grill which provides cooling coming from the plenum, which is kind of cooled air coming from the chimneys, which kind of feed the floor. To the top, you can see a white kind of a margin. That margin is a acoustic vent, which vents stale air from the office floor through the glazed partition into the atrium. The atrium is glazed really to provide some quiet space. So we did toy with the idea of having initially an open atrium, but with the activity in the basement, if you imagine 150 school kids chatting away, it probably won't really work that well with people trying to work quietly in the office. So we provide a single glazed screen to the atrium, but still provided a ventilation path from the office to the atrium. So the stale air comes into the atrium, goes up the atrium, through the vents you can see from the timber and up to the top, and then it's heat recovered. Next slide. So the third floor plan sort of shows our seminar spaces, which are our teaching spaces. So public are welcome to come up to the top floor as well for lectures and talks. And the lectures and talks are open to all the public, so anybody can go to a physics based lecture. Next slide. So John will touch on the fabric elements. So you can see the view of the atrium, the oak grills. So the palette is fairly simple. It's a concrete, white plastered finish, and the oak paneling, which is providing acoustic baffling, but also the ventilation path for the air coming out from the office floors. And the right-hand side shows Valve Street, which was retained, and then we've used reclaimed bricks for the facade, which is new, and then lightweight zinc paneling on the upper floors. Next slide. So just to these images on the image on the top left, so it shows the view from the upper floor, so you can just see a glimpse of the community garden. So all the office floors, seminar floors, and the exhibition floors get a view of the community garden in the distance. So you get light from that, you get a view from that, and something which also the atrium does is sort of provides a communication where people can see what events are happening and the activity in the building. Okay, and the right-hand image again shows all the floors. So from each floor you can see activity and also what's happening in the exhibition space. Next slide. So I'm going to hand over to John from ACOM, who's going to go through a lot more detail in terms of the key elements we've used in the sustainability kind of features and how they've kind of worked. So the BREEAM certificate sort of shows that we've got BREEAM Excellent, and he will run through the data of that now. Right over to John.
Thank you, Harish. So we can nudge on to the next screen, next slide. Okay, so I'm going to talk about some of the key principles of the engineering design. Harish already talked you through generally some of the strategies. Now, one of the first things at the beginning is this, same as the first presentation, the Untitled Steel building. We were designing this for an owner operator. So, you can have certain conversations and, and have certain systems that you probably wouldn't have with a commercial developer. So perhaps maybe longer term and in operation reviews rather than just like pure sort of hard-nosed commercial approach to things. So think about that. The brief we had and discussions we had with the client at the beginning to have well-functioning flexible space. It should be an experimental building that Harish mentioned to showcase physics. But the technology we use must be appropriate. They're nothing too crazy. It is a functional building. It's fundamentally an office space that Institute of Physics has to use. So all the technologies we're using are they're tried and tested, but they're brought together and integrated with the architecture in a kind of really nice way. And it's not a huge site, so everything had to be really well coordinated. And they wanted it to be highly sustainable. So again, the first presentation talked about the trade-off between upfront carbon emissions and operational. So we had similar sort of discussions, although they weren't necessarily quantified in quite the same way as the presentation earlier. So those were discussions that we had. So the first thing you do before you throw any engineering at it is you try and reduce or any engineering kits, you try and reduce the demand in the first place. So with that, we worked with Harish's team to come up with a fabric specification that is a very good new build spec. Large chunks of facade were retained. That was brought up to spec. Harish's team worked the details on that, and then the rest of the building obviously is new. So if we can nudge on to the next slide. Right, so flexible and adjustable internal comfort criteria. So this comes from almost like this is a sealed box in terms of mechanical ventilation, but the control strategy is more of a natural ventilation. So we allow the peak summer temperature to drift against the like a weighted mean of previous few weeks temperature. So I use the analogy that, you know, when you go on a holiday, you spend a week on the beach, the first few days it feels hot, but then after a week your body adapts. Blood thins, and you know, you feel a lot more comfortable. So during peak times in London, you don't want to be running a building at 24 degrees. You want to allow the internal temperature to drift, which is a control strategy that we have set on the building, and it significantly reduces the energy demand of the building. Also, we set quite an ambitious low winter temperature. The example I use is, in New Zealand, I understand the average indoor temperature in a domestic home in the living area is 16 degrees. New Zealanders aren't any physiologically different than we are. They're just used to lower temperatures and probably wear more clothes. So we set 18 degrees as the winter temperature, although we designed the systems to be able to cope with quite a lot more than that. As it turned out in reality, when in our post-occupancy works with the institute and their facilities team, we did have to raise it up, but we still managed to get it down with education and discussing with the staff, a lower winter temperature. Okay, next slide. So radiant cool. This is a concrete frame, concrete structure, and this gives us the ability to use the it's not an active building, so there's no embedded pipework, but the concrete slabs do emit an amount of radiant cool. So this gives the perception, increases the perception of comfort. So you can have the actual air temperature drifting up, and this little bit of radiant cool helps offset that. So this goes in concert with the drifting air temperature I talked about in a previous slide, and keeps the perception of comfort better. So if we go on to the next slide. So thermal mass. Again, this kind of similar conversation to the first one. This is a concrete structure. We have a lot of thermal mass, so we use it. Reducing our operational energy and carbon emissions. So the way it works, here's a graph which demonstrates the strategy, or this is not actually of the Institute of Physics. So the green graph shows the external temperature. The blue plot is a lightweight building, and the red plot is a heavyweight building, such as the Institute of Physics. So you can see you increase the lag, so the peak moves further on down the day. So by the time your peak comes, so the external temperature is already dropping, so you reduce the peak, and also the area under the graph is your kilowatt hours used per day. So that is lower on the red graph than it is on the blue graph. So that's the actual energy used. And then the peak, which is the top of the graph, is your installed capacity of the plant. So actually you're reducing your installed capacity by utilizing the thermal mass, which is lower capital cost and less space taken up by our engineering equipment, which is always a good thing. If we can go on to the next slide. So natural daylight. Harry's already touched on these north lights. Him and his team, there's a fantastic whole building height north light, which brings all the daylight really nicely into the building. This, as well as providing well-being and all this good stuff to the occupants, does allow us to utilize a daylight saving strategy with the lighting, so as well as reducing the energy used. So come on, next slide. So optimized lighting, natural design. So we did a lot of modeling on the lighting. This allows us to more accurately design the kind of position of the luminaires. So the luminaires it's like an engineered design rather than using like a grid system. So we can reduce the amount of luminaires that's energy used, and then that's actual embedded energy in luminaires in the first place. So if we go on to the next one. So I'll talk a little bit about the ventilation strategy. Harish has already summarized it, but one of the big design features we did at the beginning. So we use free cooling for the ventilation in the shoulder seasons where possible. So early on the design stage, we had to work with Harish's team to maximize the amount of kind of air transmission space, so ductwork that we could get into it. And then once we determined that, we then built some simulations to determine that if you kept ramping up this fresh air during the shoulder seasons, say mid autumn and spring, when you could have a cooling load, but the air inside the building, but the outside of the building outside is still quite cool. You can use that fresh air to cool the building, but then if we know what our duct size is, we can determine the cutoff point and where it becomes, we're using so much energy to run the fans that actually it becomes more efficient to switch the cooling coils on. And then you bring the fan volume right down and you switch the coils on. So we determine that approximate crossover point, and that's what we designed our engineering systems around. And that's we can only do that by really working very, very closely with Tate Hindle at the early stage to understand kind of really what was available, because we've got some really absolutely sort of crammed up floor spaces in there, or underfloor spaces in there. Okay, next slide. So we've got a closed-loop geothermal system, which provides it's a hybrid geothermal-led system with boiler backup. So we provide 100% cooling on this, and we are able to provide the vast portion of the heating on this. Now, bear in mind, this design was started about 5 or 6 years ago, when it was much more difficult than nowadays to do an electricity-led system. So we have the gas boilers in there, so which allowed us to get it through the Part L compliance. And even then, we still managed to beat the Part L 2013 by 30%. So it was a system in some ways a little bit ahead, because we are now able to operate on almost 100% of the time on electric only. And if we use the current carbon intensity factors that actually exist in the grid, rather than the notional ones that were in 2013, the building really performing very, very well against the notional. So, and as Harish talked about, there was a bit of a planning condition that we also were not allowed to have heat injection units on the roof. So it's one of the things that focuses an engineer's mind, is if you've got no backup with heat injection, you've got to design your systems to be able to cope with that. So, next slide. I know we're supposed to finish at 11:05, so I'll speed up a little bit. So the closed boreholes, this is the first time this particular system has been used in the UK. It's a geocoax system. It's about half the depth of traditional boreholes. They're quite a lot wider, and the way they manage to be shorter is that you basically have a greater surface contact area between the water and the ground. So you've got these agitators inside them, which makes the water a little bit turbulent. So it gives you really good transfer between the energy. These boreholes are energy piles and the ground. So you just reduce the kind of mass of ground that you're conducting, that you have to conduct heat into. We validated these. We looked at previous examples, and we're happy to recommend them to the Institute. The practical on-site benefit, particularly on a constrained site, is that you halve the amount of actual drilling time. So they're half the depth. So they had a program advantage. So that's one of the reasons why we chose them. So if you've just gone to the next slide. So the BMS, as Harish has mentioned about the display screen in the entrance, so which demonstrates some of the data. This was another one of the things that we were discussing with the Institute from a very early stage. They wanted to have a building which not necessarily carry out experiments on, but that you could use to study and analyze and work with their affiliate universities for them to carry out studies. So we worked with them throughout several stages of design to build up a specification for a BMS, which would fundamentally run the building in a traditional way. There's nothing too complicated about it, but it would also monitor points and things throughout the building of an order of magnitude greater than you would normally have for building, for example, relative humidity, temperature, CO2 in all the occupied spaces, energy monitoring, position monitoring on all the fans, flow sensor on all the primary distribution, which could then be stored in a data lake, and then that then extracted for study for postgraduate and PhD studies to understand more about physics and the dynamics of how a building operates. So that is the last slide I have.
Great. Well, thank you very much, Harish and John. And now we'll go on to a few questions. And if you do have them, please put your questions into the Q&A panel. But I just had a couple of questions I'd like to ask. And Mark, at the beginning, you talked about the end of raised floors. Can you just talk about that a little bit more, because that seems to have quite a lot of implications in the way that both you refurbish buildings and actually the need floor to ceiling heights needed for new buildings even.
Yeah, I mean, I think it's a huge opportunity. There's we calculated the amount of embodied carbon in the tiles. Our first hope was that we could avoid them altogether, and the desk layout allowed us just about get perimeter trunking in terms of power to the desks. Wi-Fi is pretty much universal in offices now. We do need to hardwire some of the PCs still. It was really the air conditioning and the crossovers for the kind of comfort cooling where we struggled to incorporate it. But I think if we had more time, we probably could have done it. I think it's definitely something for the future, with battery technology bringing power to people's desks or around the office. But if buildings out there can suddenly gain another 150 mil of floor to ceiling height, not putting it in the first place is the obvious thing to do, and kind of go back to hard floors or screeds. I think it's definitely the way things are going, and I think an industry will evolve from that going forward.
Thank you very much. And Harish, I was quite interested to ask you, John talked about the fact that the client didn't want to sort of push the boat out technically, but it's interesting that you showed very advanced sort of technologies being exhibited in the buildings. Wasn't there a thought that maybe you could really do something more, might say, adventurous in terms of the physics of buildings for a client like that?
I think that captures that they were open to utilising new technologies, but as physicists, they want to see that it does work and it will work, and whether that needs to be replaced. So there were several options sort of taken up. I think the key one was them being open to use borehole cooling. The first one in this in the UK. Obviously, they didn't know about that, so we had to demonstrate that could work, even though there's not much evidence of that being used in the UK. So I think those sort of features they did look at. They looked at other ones where they could sort of trial it. And I think they want to just have different technologies where it can be sort of plugged in and plugged out again. So I didn't want to have a building which was effectively redundant. So some things are firm in the kind of shell, and some things could be sort of changed. Like the thing I mentioned about the Li-Fi, something they've trialed there, and the prototype in the incubator is something which I suspect, to answer Mark's point, you won't really need to hardwire your PCs anymore, because you'll have enough speed in your in the Li-Fi system which way outperforms any cabling. So they're sort of thinking ahead.
Thanks. So if we go to our Q&A panel, which is sort of filling up at the moment. So the first question is, say, a peculiar case study showcasing an uninsulated office. So yes, perhaps maybe Andrew or Laura, I could we could discuss that. Was there any thought in providing any insulation to it, or?
I think no is it's the blunt answer. We just love the texture of the material, and I know it's in some respects it kind of goes against the the overall carbon story of the building, but generally people sleep better when it's colder and people work better when it's colder. So wear a jumper, and in the summer I think is a much bigger issue. I think we have a cross-ventilated building, and buildings just, I don't know if they are, I'm not an M&E engineer, but they just feel cooler when you have exposed brickwork.
Another thing to consider is that adding insulation does also add embodied carbon, and it is a significant life cycle maintenance, and it's got a module C aspect as well. So it's not just a net gain to just throw up some insulation. It has to be balanced out with the whole life operational and embodied carbon altogether.
Great, thank you very much. Now we have an anonymous attendee who says, how are the Institute of Physics chimneys used in extreme cold and hot weather? And also a question as to, don't the chimneys want to draw air out naturally through a stack effect? Which one, who would like to answer that one?
Shall I answer that?
Yes, please, thank you, John.
Yeah, so in hot and cold weather, the chimneys draw down the building down to ground floor, and then to little air handling units in the floor void, where we've got switch over heating and cooling coils alongside the heat recovery. So the air is tempered before it enters the end of the building. So, you know, on a day like today, we wouldn't be flowing 1 or 2 degrees centigrade fresh air into the building. What was the second question again?
And it was about whether the chimney wanted to draw air out naturally through a stack effect.
Yeah, so we've got louvres in the chimney, which when there's wind, diverts the air down, so it provides a little bit of positive pressure. And I've probably already answered the second part of that second question by saying, you know, we've got the air handling units there, so you've got a little bit positive pressure, and a little bit of negative pressure, so a little bit positive naturally, and then the air negative pressure from the air handling units in the floor void. And then remember, the air is drawn down those chimneys into the floor void and then back up out of the atrium. So there's the whole air flow through there, and in the atrium, the air is hot or warmer. So that will have a more positive buoyancy or stack effect, buoyancy effect than the chimneys. So there is a natural draw through there, and the air handling units in the floor void assist that and control it.
Thank you very much.
Okay.
So Kim has a question for HTS. As you're the owner occupier, have you found that you've been able to implement greater measures to reduce carbon? And have you had difficulties in convincing clients on other projects that timber is a viable material for the structural frame?
I'll start by picking up on that. I mean, we always wanted to do a timber roof extension, a mass timber roof extension. So there was never any optioneering really for us. We knew sustainability, from a sustainability perspective, it was the right thing to do. We had to resolve the fire issues. Yes, it is becoming increasingly challenging. We do a huge number of timber frame buildings and office buildings, and the change in regulations earlier this year, it requires a lot more work, and there are only certain consultants, fire consultants you can work with who can prove it. So there's a lot of a concern at the moment, I think, when it is proposed. But the key thing is to have the right team in place at the outset, both engineer, fire consultant, so you can take out those risks and interrogate them before it kind of runs away of itself.
Yeah, I just agree. emergent legislation aspect of it, and especially this year, London Fire Brigade, but just understanding, one way is you're looking at a charring method, but encapsulating CLT, but you lose so many other benefits and all the carbon, but actually understanding the burnout methods and how you do that. And I think legislation is moving, there is more testing, and I think there is more comfort, but as you say, just getting it at the very start, very clear what we need to consider.
Thank you very much. More Institute of Physics questions. First of all, how deep were the boreholes? And also for the Institute, there was no mention of embodied carbon. As we move into whole life carbon, it would be interesting to hear what was undertaken on that front. Who would like to respond to that?
Should I answer that? So the borehole was about 60 meters. Okay. And did we do embodied carbon calculations? I don't believe we did, Harris, did we?
No, I think that's kind of an ongoing thing to see how the embodied carbon and the operational carbon kind of will offset. Because the Institute are going to be in that building for over 25 years. They bought the building, so they're not a tenant. I think they, as an Institute, will be there for longer. So I think there's more opportunity to balance out the operational carbon with the embodied carbon, because the structure won't be changing. There'll be very little change in the building. So yeah, that will be an exercise which I think, as the building has been built for about a year and a half, with the monitoring of the building with the universities, that's a calculation I think they'll be doing anyway, to see how that balances up and what the predictions are from the design versus the actual performance of it. So they'll be monitoring performance year on year.
Thanks. Now, Jack Scar asks, is on Chart Street, what was the modelled embodied carbon for the timber structure during the demolition phase of 16 Chart Street? What is foreseen for the reuse and recycling of the timber?
So for the module C phase of the timber, it's assumed that all the biogenic captured carbon is emitted, so it becomes an embodied carbon at the end of its life. So timber has has a net negative module A, but it has a net positive module C. So it balances itself out, which I mentioned in my part of the talk, that the sequestered carbon is temporary. So once you've demolished the timber, that carbon escapes back into the atmosphere. And there's also a relatively smaller embodied carbon associated with the method of disposal. So if you recycle it, or if you reuse it even, or if it goes to landfill, there's a bit of an extra embodied carbon on top of that. But the bulk of the module C is due to the sequestered carbon that gets released into the atmosphere. And sorry, the second part of the question was?
What is foreseen for the reuse and recycling?
Yes. Well, since it's 60 years ahead, or at least 60 years ahead, hopefully more, we don't really know. But current stats from, I think, 2018 has for wood recycling and disposal in the UK has about 30% downcycled. So that's kind of turned into wood chips or into particle board, that kind of thing. About 45% burned for biomass, and then the remaining percent is unaccounted for. So that's from the Wood Recyclers Association for wood recycled in 2018. So the hope is that we'll move more and more towards reuse rather than downcycling, or obviously not landfill and biomass. But again, it's so far ahead in the future that we're really not sure.
I think one thing just to quickly add is that the circular economy is definitely a very valid consideration, but we really should be designing buildings which we foresee as being there for hundreds of years. It can be, the good thing about CLT is, certainly on Chart Street, the plank lengths are at least 5 meters, more like 7.5. They're very easy if you wanted to reuse them, to lift off and cut down. So as an element, it's very reusable, but really we should be designing things which are adaptable, not reusable.
Great. I think that the building shell is there and right, and then it stays there for longer. There's no need to kind of knock it down again.
Thanks. Now there's a question here about the answer you gave a few moments ago from Christian Felber, who wants to ask which fire consultants actually are good on timber structures. So are you willing to
I can
disclose?
name a couple. I mean, there are a few. If anyone who follows our webinars will know, we did one recently with OFR fire consultants who are very well. They collaborate a lot with LFB and a lot of their testing, and they're good. But the key thing is, as with anything like this, if you're getting a competitive tender or 2 or 3, make sure they can all do what you need it to be, and tell them what your intention is at the outset. Your intention is to have a mass timber structure, and your intention is to expose the timber. That's the really key thing, and that they can all do it.
Great. Thank you very much. Now, just one last question for Harish here. Do you see any improvements within consenting planning approval process that would have assisted to implement the various low carbon construction techniques and measures discussed? So is there something the planning system needs to respond to on them?
Yes, I think they do. I think from the discussions which we've had recently with planning authorities, with City, Westminster, Islington, there is a conversation about the sustainability of a project. 5 years ago, when we talked about this scheme, that was discussed. But what was more important to the planners there was conservation, the area and impact. So I think the scheme was modified in some ways, made slightly less sustainable to deal with the conservation issues. I think now the pendulum has probably swung the other way, where I think the key features of the chimneys and other features would have been probably welcomed more now than they would have been in the past. So I'm hopeful that seeing adaptation and retrofitting buildings, and there's more openness about taking these on from the planning and conservation authorities.
Great, thank you very much. Now we're just about getting up to time, so I'd like to thank all our speakers for their contributions, and great to go out on site, and thank you all for watching. And I would add that on Friday this week, we will have a technical competency briefing on the Building Safety Bill. So do register for that on the NLA website if you want to join. And now we will also be putting onto the screen in a minute a little question for you to answer about your experience of watching this program. We'd be very glad if you would fill those in, because it really helps us to improve our programs going forward to suit our particular ones. So there it is up on your screen, and I'd like to once again thank our speakers for great presentations, and thank you all for being here today.